Okay, so welcome to Math 344, Math of Sports. This is lecture 6. And so today we're going to talk about misleading statistics. I almost feel like we don't have to put misleading in when we talk about statistics. There's so many of them are so easily misinterpreted. We will discuss a little bit more the Fredonia-Slovenia problem, and we will go from that to Markov models for baseball, and then we'll discuss presentations. So for those of you who are just coming in, the only thing I have mentioned is we'll be talking about misleading statistics. As a tip of the hat, because you were the one who actually gave me the misleading statistic. All right, so this is a tweet. Laker championship odds last week plus 5,000. Laker odds after dumping Westbrook, acquiring Russell, Beasley, and Bamba plus 5,000. It's not getting easier for Lakers fans. How do you interpret that tweet? Yeah.
Other teams got better too.
Right. So one way of saying is, well, other teams are getting better as well. As the trade deadline approaches, you don't have teams saying, geez, how can we field a worse team? Or maybe you do. Who might be saying, how can we field a worse team? Yeah, teams at the bottom that are trying to get really good draft pick. You have an incentive to actually have a bad season. And so if the season is already gone, you might say, look, maybe we can sell some people now, people who are close to their contract running out, get something for them. And then, so when you see this, it's not getting easier for Lakers fans. Implicit in this is the fact that the Lakers did not do a good job in the trading. And I'm curious as to how people view this. Do you view this as this is a criticism of the Lakers? So how many people think that this is criticizing the Lakers? Okay, so if you view it like that, the other teams that are in contention are also trying to make trades. So this is saying that the Lakers at least lost no ground. So that as the trade deadline approached, they didn't lose any ground relative to the other teams. So I think it's actually possible to view this as, the Lakers did an okay job, not a great job. You would hope that they would gain ground on their competitors, but they at least did not lose ground. So, to me, I'm being brutally honest, I don't really know how to, read this. Of course, you also have, the Laker with the head in the hand, which does have a negative connotation. And so it would be interesting if people's view of the tweet would be different depending on what they're showing over there. But again, there are so many stats that are just bandied around. You've got to be careful as to what do they mean. Implicit in this is that the Lakers did not lose any ground as the trade deadline hit. All right. So my go-to programming environment these days is Mathematica. When I was young, I used to program in real languages. For the most part, I've gotten lazy. Mathematica has a lot of really nice built-in functions. And so, I entered the matrix A, 0.8, 0.3, 0.2, 0.7, and then matrix form displays it in a way that humans can actually read. How many of you have used LaTeX? Can you just look at LaTeX source code now and see what it says? How many of you have seen the movie The Matrix? Where Cypher goes, I don't see, the code anymore. I just see, the various people. That after a while, you just get used to looking at things. So when you're using some of these environments, it's often not a bad idea to take some time and format things in a way that you can actually make sense of. And we'll see a much better example of that in a moment. But this is the matrix 0.8, 0.3, 0.2, 0.7. And Mathematica's beautiful command, eigenvalues A, eigenvectors A, find the eigenvalues, find the eigenvectors. This is the 21st century. I'm not doing these calculations. And so, not surprisingly, it's 1 and 0.5, and then there are these corresponding eigenvectors. Do you think those eigenvectors are exact? No. These are not exact. And the reason they're not exact is it's doing numerical computations. Does anybody know how I could have gotten the exact eigenvalues and eigenvectors? So instead of having 0.8, 0.3, 0.2, 0.7, if I did 8/10, 3/10, 2/10, 7/10, it would then work with everything I believe fully accurately and would not be doing any numerical approximations. These are actual numerical approximations at the end. I believe if I just wrote things as rational numbers, it would be fine. All right. So let's modify the problem a little bit. So I'm going to form my new matrix A of x, y, where I'm going to subtract x from the point 8 and therefore add x to the point 2. And I'm going to subtract y from the point 3 and add it to the point 7. So this is changing the rate at which people stay and leave. And I can change it in each country depending on how I want. And so now I can look at the family of such problems. We did the specific case when x and y equals 0, but what happens if I put in different values for x and y? And so here's my matrix, and I can calculate the eigenvalues and eigenvectors. And again, I could probably do a better job if instead of doing 0.8, if I did things like 8/10. And then Mathematica would do exact calculations rather than numerical ones. And so when you look at the outputs, what do you see? So these are my eigenvalues, and these are my eigenvectors. And then just for simplicity, so I can use them later on, I took the largest one, the largest, and I created a new function for that, and the smallest one, I called it smallest. How do I know which one is which? Well, the difference is this has a plus sign and this has a minus sign, so this is clearly going to be the largest. Or did I get it wrong over here? I might have flipped things. Bless you. Oh no, these are the eigenvalues coming up over here. The minus and the plus. The pluses. So did I switch them over here? I think I might have switched them over here. Okay, I'll fix it later. I did fix it when I plotted things. When you look at the largest eigenvalue, what do you see? So this is the largest one over here. What do you notice about it? So it's a function of x and y, right? Does that make sense to anybody? Can anybody tell me anything about the largest eigenvalue? So no one can tell me anything about the largest eigenvalue. What if you choose a special value of x and y? Can you tell me something about it? Are there any values of x and y which we know? Yes.
Well, they exactly looked at earlier was when they're both 0.
Good. When they're both 0, the eigenvalues are 1.5. So we at least know what's going on when x equals y equals 0. What about more general x and y? All right, so if this is not speaking to you, what could you do to try to get a feel for it? I'm sorry? Get some plots. Oh, what a coincidence. The next slide happens to be a plot. So here's a plot of the largest eigenvalue. What do you notice the largest eigenvalue is? X goes from minus 0.2 to 0.2, y goes from minus 0.3 to 0.3. And the reason is I don't want to have 103% of the people stay or -% of people move out. What do you notice about the value of the largest eigenvalue? So if you look at this plot, what do you see? What is it? It looks pretty constant. What does that constant value look like? 1. Well, if you look at the matrix again, let's go back. So if you look at the matrix, what is the sum of the first column of the matrix? What's the sum of the second column? By the Bula-Bula theorem, since the columns all sum to 1, 1 is an eigenvalue. This is the whole point of the danger of mathematical formula. You might actually have something that you can understand completely, but it's presented in a very misleading manner. I just wrote the function 1. So there must be some way to do some algebraic simplifications that will turn this into 1. There's got to be, right? So as a nice algebraic exercise, see if you can prove that this is 1. We should have been able to recognize immediately that it has to be 1 because the matrix still has the columns summing to 1. But the information was presented in such a way that we didn't see it. Well, what goes on if we don't see something? Well, we try to find ways to represent it in a way that will highlight what's going on. And this is why I plotted it. Okay, once I see that the plot, the plot looks constant. That's a pretty big hint of what's going on. Now that I know it's constant, I can now go back and say, there must be an algebraic way to show that this equals 1. And so if I know that this expression equals 1, I could basically say, let's set this equal to 1. Let's bring this over to the other side. Let's square things to get rid of that. And that probably should work. And then once it works, what you then do is you then just write the steps in reverse order. How many people have taken real analysis? What's a 3 epsilon proof? You have some expression, you're trying to show that it gets very small. You often break it up into 3 parts. This part is less than epsilon, this part is less than epsilon, this part is less than epsilon, so the sum is less than 3 epsilon. Technically, if you want to look, fancy, your thing is supposed to be less than epsilon, so you adjust things in the beginning to have each one less than epsilon over 3. So a lot of times when you're doing these proofs in real analysis, you'll have these strange constants coming in because you know at the end you're going to be combining them in such a way that the final expression will be less than epsilon. It's not really a big deal. When you're trying to prove something, pattern recognition, if you know what it is, that can help guide you with the algebra. I think you can just write it in reverse order and just hide from people how you actually got there. If you know that this equals 1, it makes it a lot easier to know what algebra to do. What about the smallest eigenvalue? Does that look like anything that you can make sense of? So here, this should be just. Does the smallest look meaningful to you? What should we do? Plot it. And not surprisingly, and so I plotted it 2 different ways. And here you can clearly see that there is a difference in behavior. And so the first one is just a standard 3-dimensional plot. The second one is a contour plot. So each line here, all these values are the same. And there's a little key here to tell you what they are. And so again, so much of it comes down to, can you find a good way to understand what's going on? All right, so let's go back to the original version of the problem. So here is the original version. It's not letting me paste. All right. I'll just try it here. We have our 2 eigenvalues, 1 and 1/2, and we have our 2 eigenvectors. Let's call it v1 and v2. What can you tell me about v1 and v2? So v2 is negative part. V2 is going to be something like this, and v1 will be something like this. What can you tell me about v1 and v2? So we need a little bit of linear algebra knowledge. Yes.
They have to be linearly.
Excellent. So they're linearly independent. So I can write any v as C1 v1 plus C2 v2. And so if I take a high power of my matrix A, and I apply it to V, that's going to be C1, 1 to the n, V1, plus C2, 1/2 to the n, V2. So as n goes to infinity, what does a and b go to? It just goes to C1, V1. Because the second term has a 1/2 to the n, that's going to go to 0. So there is actually going to be a steady state. It's going to just become, C1, V1. Now, we have to prove, of course, that C1 is not 0. If C1 is 0, what would happen? So what would happen if C1 is 0? What would A and B go to? So if C1 is 0, what would A and B go to in the limit? It would just go to 0, which means everyone's dead. We're in this idealized world where no one dies, no one is born. People just move between Fredonia and Sylvania. So it's absurd for C1 to be 0. When we're looking at writing V, these are initial conditions. So your V is the Fredonia at time 0 over the Sylvania at time 0. That's what V2, that's what V is. It's the initial population. Well, if I look at the initial population, if C1 is 0, V2 has two components. One is positive, one is negative. There's no choice of C2 such that I could have my initial population vector being only in the direction of V2, because I start off with people. So I know that C1 has to be non-zero. And if you think about it, the components of V2 are opposite. It's basically saying people are moving the net flux of people from one to the other. And so there will be a steady state, and that steady state is going to just be determined by knowing what that initial constant is, C1, to write it as C1 V1 plus C2 V2. If I were to change the matrix, that's going to change the other eigenvalue here. It's not going to change this eigenvalue. The analysis is going to be extremely similar in general. This is still going to go to 0. What will change is how rapidly it goes to 0, and it will change C1. So what we would really love to do is we would love to go to here, and we would love to, V as, C1 X, Y, V1 XY plus C2 XY V2 XY. And how does that, C1, V1, how does that change as I vary those numbers? Because it's small, it's only degree 2, it's quadratic, we can actually do all of this. As you get to higher and higher degrees, as you have more and more countries, we're not going to be able to write down closed form expressions like this. But again, when you're trying to understand things, try to do the simple case as well as you can. There is a danger sometimes that when you look at a simple case, you will have so much available that you'll actually be able to do better there, and you can't generalize it. I will say it happens. But if you can't even solve the simple case, you're going to have no chance in the general case. Or you might just step back and say, what am I willing to consider as a solution? Okay, so let's go to the problem you're supposed to think about. If I give you the run expectancy matrix, can you figure out what the transition probabilities are to the various states? So the reason I care about this problem is, the general principle is a lot of times we don't always collect all the information we want. And then you need to get more information. Sometimes it's impossible. Who here has ever looked at a box score of a baseball game? Now, if the baseball game has been recorded, you can actually just watch the tape and see what happens, right? And so if you want more information, you can just go through and do that. For games from the early 1900s, we don't have these games recorded. And so depending on what you get for the box score, you may not be able to reproduce the game. If they give you the play-by-play, that's not a big deal. There actually is a book of puzzles. How many of you have ever seen chess puzzles? Where they give you box score puzzles. They give you a box score, and you're supposed to try to figure out what happened if this is the box score. And in some situations, you can actually figure out what's going on, not surprisingly, in these situations, because they're trying to make it interesting. Other times, there's more than one thing that could happen. And so for some of the old games, we have no way of being able to reproduce what went on. How many people were on base when this person was getting hits? We know how many RBIs they had, so we might be able to figure out somewhat who was on base or not. But if you're trying to figure out, is there such a thing as clutch hitting? Do people hit well in pressure situations? If you look at the box score, it might just tell you how many hits somebody had in the game. It might not tell you, was it early or late in the game? Were there runners on base? What was the score? And so there's a lot of information that's just lost from how it's stored. This is the 21st century. Is it a big deal to store information? How many people have a phone? How many people have pictures on their phone? How many people have more than 100 pictures on their phone? More than 1,000. Yeah, is it a big deal to take a photo? When I was young, my first camera had a little cube flash and film that you would feed in. And it's like, do I want to waste a shot on this? I've got 6, 12, 24, maybe 36 shots, depending on what film I'm using. And video, when I was a kid, we had 3 to 5 minute clips from 3 or 4 different Disney movies, and some of our family members had 3 or 4 minute clips of other Disney movies, and we would just rotate amongst ourselves. And if someone was having a birthday party, all right, we've got Song of the South and Snow White and Sleeping Beauty. Oh, you have this. We'll put them all together, and we might be able to get like 20 minutes. This was before VHS even. This is the 21st century now. You have so much information now that it's not so hard to just gather more data than you think you might need, because later you might decide it's important. That's the big thing I want you to get from today's class, is that you don't always know what's going to be useful. Later on, you might discover, hey, there was this really interesting relationship, and I need more data. So when you look at, okay, I know we've got some hockey fans here, plus minus statistic, right? Good statistic, bad statistic. What do you think of the plus minus? So how many points does your team score with you on the ice, minus how many points you allow? And they do this also in basketball. What's good, what's bad about the plus minus statistic?
It doesn't incorporate how relevant you specifically were to the goal for, yes.
Good. So it doesn't take into account what you yourself are doing. If you coach little kids, you might have somebody who's just tying a sneaker as the play goes on. What else does it not take into account?
Like how good your teammates might be making you look.
Yeah, so who's on the ice or the field on your team, as well as who your opponents are. So the plus minus statistic, it's easy to use, but there's a lot of information I would love to have. Well, if I have a complete record of the game as to every moment every person was in, I could then look at an augmented plus minus statistic that takes into account, do I have my first string in? Do I have my second string in? What about the opponents? And then with that extra information, we could take the very simple plus minus statistic and make it much, much better and see, the team has a huge plus, but it was the end of the game. The team was already up by a lot. The other team had decided to rest their starters and put in other people. So you can have much more information. So what I want to do today is I want to try to figure out, what can we deduce from a run expectancy matrix? Can we figure out what the different transition probabilities are? If you look at a baseball card, the baseball card will tell you You know, how many plate appearances does someone have? How many at-bats? So, you know, differences between plate appearances and at-bats are things like walks, hit by pitch, stuff like that. How many singles, doubles, triples do you have? But it will not tell you how many times when you have a single do you advance a runner from first to third or from second to home. So, you know, stuff like that is completely missing in a baseball card. We can keep track of all that information throughout the season. You know, again, the baseball card is just giving you a snapshot. If we want to try to model a baseball game, you know, we did the Fredonia Sylvania. This is a really simple model. It's completely deterministic. There's no uncertainty in what's going to happen. At every moment in time, 80% of the people in Fredonia stay, 20% leave, 70% of the people in Sylvania stay, 30% leave. We just have to do the calculation. We know what's going to happen. We don't have that in sports. You know, if we did, sports would be very boring. What we have is we have probabilities of events happening and consequences. And so if I give you the run expectancy matrix, is there enough information there to recover what happens? And I think we said we were going to consider a simplified baseball game where you have home plate and just one base. And for outs, there's either 0 or 1 out, right? So is this enough? If I give you the expectancy matrix, so we have 0 outs, we have 1 out, we have nobody on base, and we have 1 runner on base, right? There's only 4 possibilities? Yes. And so what we need to do is, you know, give us the different values. So let's say maybe R11, R12, R21, R22. Do you want to do it like that, or do you want to do different notation? I think there's a better notation than that. Instead of R11, what might be a little bit better?
0, 1, and
Yeah, maybe do 0, 0, 0, 1, 1, 0, 1, 1. Always think about the notation you're going to use. Take a moment, think about it, and then go forward. And if I do it like that, well, now the subscripts are telling me the game state. You know, the first one is going to be the number of outs. The second one is going to be the bases. So let's say I actually give you this. Is this enough information to deduce what the transition probabilities are? So we've got to write down the different states. So we could have 0 outs, 0 on base. We could have 0 outs, 1 on base. We could have 1 out, 0 on base. We could have 1 out, 1 on base. Okay. Is it possible to go from 0 out, 0 on base after batter back to itself? Yes. Home run. So there actually is a probability. So P00 home run, so we have to add 1 run. So that would be the transition probability. And now we have to decide, how do we want to denote this? So one possibility is I could denote this with 4 subscripts. The first 2 is the initial state, the last 2 is the final. Or I could give the 4 states just different names, A, B, C, D. Which do people want? Do you want to have 4 subscripts, or want to do A, B, C, D? So I could do 1, 2, 3, 4 for the 4 states. Let's do 1, 2, 3, 4. So we'll call that 1, 2, 3, 4. So this is going to be P11. Can you go from 0 out, 0 on base to 1 out, 1 on base? No. So we would know that P14 equals 0. Could we go from no outs, none on base to no outs, 1 on base? Yes. So that would be P12. We could go from no outs, none on base to 1 out, 1 on base. That'd be P13. Okay, is that all the different stuff going from no outs, none on base? Okay, what about if we have no outs, 1 on base? Can we get back to that state? Base hit. So we could come back, and then that would be P22. And what must happen in that case? 1 scores. Okay, can we go from no outs, 1 on base to 1 out, no one on base? So how would that be?
Double play.
Well, if it's double play, the inning would be over because two outs ends the inning. But we have to have no one on base.
Does
Yes.
the ball have to be put in play, or it could be like a pickoff or a caught stealing?
So we're going to keep things simple. No pickoffs, caught stealing. Sack fly. And a run scores. So again, if we were to actually analyze a real Major League Baseball game, it would be a lot more complicated because the sack fly could just advance a runner from second to third. It may not actually score. But you could go from no outs, 1 on base to 1 out, no one on base because the runner scored. It doesn't actually have to be a sack fly. It could be, oh no, because we have nobody on base. The run has to score. Okay. Could we go from 0 outs, 1 on base to 1 out, 1 on base? Yeah, just gets out. So that would be fine. So that'd be P24. All right, we're halfway there. Can you go from 1 out, no one on base back to 1 out, no one on base?
Well, should we still look at if we can go from?
Oh, sorry, from 0 outs, I forgot. 0 outs, 1 on base to no outs, no one on base.
Home run or double play?
We can't have the double play. Oh, that would end the inning.
Wouldn't that put us back to 0-0?
No, but no, if we have a double play, we would have 2 outs, and then that would end the inning. So just a home run. So this would then be P21, and then a run scores. Actually, 2 run scores, right? Okay, so right now we would have P11 is going to add 1. And then we just said P22 adds a run. And P21 adds 2 runs. Okay. Now have we done everything? For just 0 outs, 1 on base. All right, now we have to look at 1 out, no one is on base. Can we go to 0 outs, 0 on base? No. So we know P31 is 0. Can we go from 1 out, no one on base to no outs, 1 on base? No. So we know P32 is 0, so it's getting a little bit easier. Can we go from 1 out, no one on base to 1 out, 1 on base? Yes. So that's going to be P34. Or we forgot to look at, can we go from 1 out, no one on base to 1 out, no one on base? Yes, that'd be a home run. It would be P33, 1 run scores. So P33 would be +1. Okay, are we missing anything for 1 out, no one on base? All right, so the last one is 1 out, 1 person on base. Let's choose a new color. Okay. Could we go from there to no outs, no one on base? Nope. So we would know P 4-1 equals 0. Could we go from 1 out to no outs? Nope. So we would know P4-2 is 0. Could we go from 1 out, a runner on base, to 1 out, no one on base? So what would that be? Good. Score 2 runs. So it'd be P3-4, and it'd be +2. And then could we go from 1 out, 1 on base to 1 out, 1 on base? Yes, that'd just be a hit. And a run scores. So the question is, do we want to add another box here that says 2 outs? Because we know then things would end. So would it be useful to talk about the transition probabilities into 2 outs? So let's add it. And so, again, it's not initially clear always what you want to do. By having something that says 2 outs, eventually we should, with high probability, hit this. And by high probability, I mean, as we do it longer and longer and longer, with probability tending towards 1, we have to get to 2 outs. Okay, is it possible to go from 0 outs, no one on base, to 2 outs? No. So let me choose a new color. Maybe some kind of orange. So we would know P15 is 0. Can we go from no outs, 1 on base, to 2 outs? Yeah, that would be a double play. Right? So we could have a P25. What about 1 out, no one on base? Can we go to 2 outs? Yeah, that's fine. So that would be P35. 1 out, 1 on base to 2 outs. Now, things are a little bit simpler here than in real baseball. Do we have to worry about a run scoring in a situation like this? So you got to really know your baseball. So is it possible in this problem that a run scores? Yes.
P45, the guy on base makes it back, and then the guy who hit runs to first base and then is trying to run back and gets out on his way back to home.
So are you saying that somebody could score?
Yeah, someone like the first guy scores and the second guy gets greedy and tries to
Good.
score.
That's how it would have to happen. So in baseball, the run does not count until all the runners make it to the base that they have to get to. And so because we only have 1 base, the runner on that base could score, and the runner who was at the plate could be running, safely gets to the base, and then decides to get greedy and goes home and gets out. So it is possible that they could score a run. Let's just make things simple right now, and we will say that this cannot happen. Okay. So I was talking about officiating and umpiring with some of you before class started. And one of the crazy coaches we played against in Vermont, years ago, my daughter was supposed to be starting the game in left field, but my third baseman, well, she forgot her glove. So we moved her to the outfield while her parents were getting her glove, and moved Caleb to third base. bases were loaded, Kayla fielded the ball and stepped on third. I said she stepped on the bag before the run crossed the plate. The other coach said she did not step on the bag before the run crossed the plate. Does it matter? No, doesn't matter. The run of going from second to third, bases were loaded, did not get to the base they needed to get to. The run does not count. Rather than having a fight, we just said you can have the run. So you do have to worry about some of these low probability situations when you're making things. For the simplified version, let's just try to keep it like this. This is a beautiful picture, right? You can ask, is this the best way to be laying things out? You know, it might be better to have things in maybe like a tetrahedron, or maybe, what is the tetrahedron called? Is it an octahedron when it's on the bottom as well? No, it's not an octahedron. But you know, maybe what to do is have something like this. And then you have, you know, 3 things coming up and then 3 things going down like that. You know, in terms of just what's the best way to display it. You know, I don't think this is too bad with the 4 things here. So do we agree that these are all the different probabilities we need to worry about? Hopefully we haven't forgotten anything. And now the question is, I'm giving you these 4 numbers. Do you think that that should be enough to determine all these transition probabilities? What are your feelings? So do you think that this should be enough information to determine all these transition probabilities? Yes.
I don't think so, because if you were to say so, like sort each transition probability for 4 numbers, you don't know which numbers specifically.
Okay, can you try to explain it again? So I'm giving you the 4 numbers, the 4 R's, and you have all these transition probabilities that you want to figure out. So you're saying that there's not enough information to get all the probabilities.
You're saying we're trying to find the probability.
Right, I want to know, do these 4 numbers uniquely determine all the probabilities? Can I determine the probabilities from knowing these values here?
Well, if you knew the values, wouldn't you have to like
Which values? You got to be very specific.
If you knew the four R's.
Right, so let's assume these are known. And then the stuff, what color have we not used yet? These are the unknowns. So do these 4 known values uniquely determine these probabilities? Why not?
Because there's multiple paths. Like from 2 to 3, there's a bunch of different ways you could go, so you don't know the weights on each of them, even if though they might sum to.
Well, but that's the whole point is, does this force those weights on me? Why not?
You could set it up as 4 equations.
Okay, so we only have 4 equations. How many unknowns do we have? So let's think about it. There's 5 things, so there would be 25 P's, and I've written down 1, 2, 3, 4, 5, 6 P's as 0. So maybe there's 19 unknowns.
Oh, wouldn't there be 20 P's? Is you can only start in 48 states and end in 5 states.
Okay.
Start with
Okay, good. Right, we have nothing coming out of the last one. So maybe it's 20 and then I lose 6, so maybe it's 14. I'll buy that. So maybe 14 unknowns. So what do you think? I've got 4 equations, 14 unknowns. Do you think that I can figure out what these unknowns are? Why not? What's the key word from linear algebra?
It's called like under.
Yes, this is an underdetermined. This is just in case, anybody who's, officially tasked with the college to make sure that this is a legitimate class walks in. We go, oh yeah, we're using the linear algebra prerequisites. This is an underdetermined system. But, and there is a but that might save the day. Does anybody know what the but is? Yes.
This isn't answering that question, but don't we have more than 4 equations? Well, we have 4, like an equation for each of the R's, and then we also have that, like all the P5s.
Good. So that was half of the buts. So but 1 is we have more equations. So how many more equations do we have? We have 5 more equations. 5 more. We know P11 plus P12 plus P13 plus P14 plus P15 equals 1, all the way down to P51 plus ... plus P55 equals 1. So now we have 9 equations, 14 unknowns. So you got us basically halfway there, which was great. But unfortunately, it's still underdetermined. There is a second but. So I'm going to get it slightly wrong, but there are, hopefully somebody here can help me. There are these class of riddles where you're told you have some counts of goats and sheep and cows, and 3 times the number of goats minus twice the number of cows equals blah, 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 blah. And it's an undetermined system. It's an underdetermined system, but there's still an answer. Because you have to remember there's one other fact you have to remember when you're doing these problems about how many goats and cows and whatnot that you have. What's that extra bit of information? Somebody give me a number of possible number of goats that you might have. 7. Good. Give me another possible number for how many goats you could have. 11. What do you notice about these numbers, other than they form a really nice convenience store? Hey, I got to monetize this class somehow, okay? What are you there? Positive integers. Has anybody heard of a timeshare for a goat, where you might have 3/7 of a goat? You get the goat Monday, Wednesday, Friday, can bring the goat to class? No. You only have integer numbers of goats. Here, each Pij is in the interval 0, 1. So it is definitely an underdetermined system, but all of the values have to be between 0 and 1. I don't think that's going to be enough to force it to be unique.
Just one question on 1.
Yes.
How can P51 ... P55 equal 1 if we have nothing coming out of them? Would those not exist?
Or maybe that should be 0. Sorry, thank you. So we do have this additional fact. So as an extra credit assignment, choose some transition probabilities, calculate the R's, and then see if I give you those R's, if it leads to one and only one solution. So start off where you know there has to be a solution because you've chosen the P's. And then see once you have that matrix R, if there can be more than one solution. So I'll make that as an extra credit assignment. If someone's able to do that, please just email me, let me know. All right, this is a good place to stop.